Hi everyone, my name is Thomas Kim. Today is December 6, 2019. This is my 45th episode about linear algebra and threading building blocks. In our previous episode, episode 44, I explained the theory behind the system of linear equation using back substitution. So, if you haven't watched this video, please watch it. Without watching episode 44, System of Linear Equation with Back Substitution, you cannot follow my current session. Also, you have to watch my all previous videos, episode 43, episode 42, episode 41. Otherwise, you may not be able to understand or follow this session. Scroll down. You have to download source code from episode 43. Double-click this link to download source code from episode 43. Also, you have to download source code from episode 41. Please double-click this link to download source code from episode 41. Also, double-click episode 44, this link, to download the source code. Or you can visit www.talkplayfun.com, download, hit enter from TBB linear algebra. You can click the file in this folder and download respective source code. Now click show in folder. So expand source code 43, unzip it, and rename it. I expanded source code from 43 and I rename it 45. Linear equations, back substitution, implementation. The folder name is 45 linear equations, back substitution, implementation. Hit enter. Extract source code from 41. Extract. In this folder, right click, rename, linear, hit enter. Copy this file, copy, paste it in this folder, 45. Paste it here. Download. Now extract 44 linear equations back substitution theory. Extract it. If you extract this folder, you can find this image file. Now select folder 45, 44, copy, paste it to your working folder. This is my working folder. Paste it. In this episode, we will implement the system of linear equations with back substitution. While implementing this algorithm, we will refer to this link, this document. We will implement sequential algorithm. If you want to know how to implement it in parallel, in TBB Pro, page 62, a slightly more complicated example, forward substitution. Double-click this link. In this book, page 65, a slightly more complicated example explains how to parallelize forward substitution. Because forward substitution and back substitution, the algorithm is exactly the same. So if you want to know how to parallelize our implementation, then you can refer to this book in page 65. In future episodes, I may or may not implement this algorithm. I tested this algorithm, parallelizing forward substitution. When the matrix is of small size, the algorithm does not give any benefits. But when the matrix is big, like millions of elements, then this parallelization gives significant performance. I may or may not implement this algorithm in my series. If there is a request, then I probably do. Without further ado, let's get started. Start Visual Studio Code. The folder is already open. Expand the folder 45. Double-click linear.hpp. Ctrl V. Scroll down. Copy this. Copy. Paste. In this section, container element type, allocator type, element type, ampersand V. This is container type. Please note that we implemented this algorithm in episode 41. In this video, we implemented this algorithm. Now here, all we need to do is just add one more line of code. Please note that V is not matrix, it is vector. So std swap v I v k. Okay, so we are swapping I low with k low. In the same manner, we are swapping vi with vk. Now scroll down. Gaussian Elimination parallel. Copy this function. Copy. Paste. Container type, element type, allocator type, element type, ampersand V. Scroll down. Here, V I AA times BK. So we extended this part. Now scroll down. Now copy this part. Copy. Scroll down. Paste. Modify it. Linear equations Gaussian. We modified the function like this. From this page, the diagonal element should not be 0. Diagonal element should not be 0. This function will return Boolean value. Step 1. Triangular lies matrix A using this algorithm. Gaussian Elimination parallel A, B. Step 2. Check if all diagonal elements of A are not 0. For size T, K, K less than A lows plus plus K. If matrix is 0, A, K, K. If 0, return false. If one of the diagonal element is 0, we cannot further proceed. From this file once again, the I starts from log count -1 up to 0 greater than -1 for int I int log count a rows. Give typecast here int log count -1 I should be greater than -1. We have to decrease back substitution. In this file, once again, this part is sum, partial sum. It runs with J's index start with +1 should be less than log count. So for int j I +1, because this is I +1, j less than log count plus j, it is increasing. I will introduce here element type sum. We initialize sum with 0. Sum, we are summing up a ij times, we are applying this rule bj. After this block, bi equals bi minus sum over a I. This is diagonal element. I am applying this rule. So everything is done. Return true. But this algorithm is not yet perfect. Copy this line, cut, scroll up, paste, int column count, int a columns, int vector size, int b size, bool log count should be greater than 0 and column count should be greater than 0 and vector size should be greater than 0 and log count should be equal to column count and log count should be equal to vector size. Bool valid. If valid is not true, return false. Or we can just say, I will change it, operation valid. Copy, paste. If operation is not valid, return false. This condition means that the log count should be at least 1 or greater. Vector size should also be greater than 0. Log count equals to column count means matrix A should be square matrix, and the log count also should be equal to vector size. Otherwise, we cannot solve this equation. With this, column count, paste it here. The remainder is the same. Now open this file, matrix2d.hpp, Ctrl V, Ctrl F, clone. Now here, copy, paste, template, type name, ELE type. template, type name, I say vector element type, class vector container type, template, type name, class vector allocator type, vector container type, vector element type, vector allocator type, vector element type. One more angle bracket, reference B. Put it constant. In my future video, we will turn it to forwarding reference. For the time being, we will use this construct. Matrix 2D augmented. This M rows, this M columns plus 1 for size T, I less than this M rows plus I for size T, J less than this M columns plus J augmented IJ, this operator IJ augmented I, this M rows plus 1 B I, return augmented. From this code, scroll up. I will copy this part, paste it here. It should be this M rows, this M columns. If debugging mode equal 1 and if operation valid is not true, talk play fun, throw debug exception, operation invalid. Matrix is either not square or the size of B is incompatible. Don't forget semicolon. I will just copy this, copy, paste plus 1. I will also paste it here. Also here, because this should be square matrix. Also here, and it should be int. It should be int. Now we created the augmented matrix. We will modify this function too in my next episode. Now we will copy this function once again. Copy. Up to this point, copy, paste. Now we don't need this term. We don't need this. Now the condition is different. I will delete this part. Row count plus 1 should be equal to column count. Now scroll down. We have to remove this. Now scroll down. This part is correct. Now scroll down. Now here, auto reference vi equals a I row count. Also here a I row count. Also here vi, or I can just copy this part. Cut, paste, paste. You can do this, but you can also do this. vi equals vi minus sum over AII. These two are equivalent. Or I will copy this, cut, I will put it here. Now the remainder is the same. If it is confusing, I will use some parentheses. Also, I will use some parentheses to make it look clear. Also in this file, I will use some parentheses. I think this part is redundant. I delete it because this part checks column count and vector size too. Scroll down, let's double check. I made a mistake here. We have to fix like this. Don't forget it. Now in linear CPP, let's go over once again. From this function, linear equation Gaussian, this part is redundant. I fixed like this. Scroll down. Scroll down. We need int because row count is type int. Scroll down. I fixed like this. It should be int. Scroll down. I made a mistake here too. It should be j. I will copy from here for your reference. So this Vj is AJ row count. Scroll down. The remainder is correct. Now scroll down. From here, I will remove before we test. I found I made a misspell here. Right click the folder, rename, implementation, dir cd 45 linear equations, back substitution, implementation, clang ++ std C++17 linear.cpp ltbb malloc, hit enter. Wow, it built. CLS. So this is the matrix. I got this matrix from Wikipedia, Gaussian elimination. If you scroll down, you can find this matrix. Close other tab. If we scroll down, this is the matrix. 2, 1, minus 1, 8, minus 3, 1, minus 1, 2, minus 11, minus 2, 1, 2, negative 3. So this is the matrix. Control B, control minus. Now here, this is matrix A. I will create another matrix B, row count. This is a square matrix. I say vector T using vector T matrix T container type. Okay. Now here vector T B row count. We define the vector. I will copy this, copy, paste. Now change it to B. B is vector. So it should be 0, copy, paste, 1, 2, fix like this. Now this is B. I will copy B. Okay. Now we print out stream, original, matrices, and vector. And the stream A equal stream, B equal output, print matrix, stream B 6. I will put 6 here. I will copy once again. This is B, and there. Let's build once again. CLS. So this is our initial configuration. A is augmented matrix. B, this is square matrix of this part. B is, this is B. 8 minus 11 minus 3. Now with this, linear, auto, AA. A copy of A. Linear, equation, Gaussian, A. In this case, we are calling this function. Okay. Second implementation. Copy, paste. Output, print matrix, stream, AA 6. First implementation 1. This is our first implementation. Here we have to pass A and B. Auto, BB, B, auto, VB, VB, V. We made copy, linear, equations, Gaussian, BB, VB. This is our first implementation 1, stream, solution 1. Now we have another way, auto, CC, B, clone. We provide V, okay? Then using second implementation, again, output, linear, equations, Gaussian, CC, output, print matrix, stream, CC, 6, stream, solution with second implementation. This is solution 1, stream, solution with second but different method. Sorry, we calculated AA. We calculated A but printed out AA, so we should fix AA like this. Let's try. We build again CLS. So this is original input and this is solution. The last column is solution. If we compare with this Wikipedia, 231 is the solution. This solution comes from here using linear equation Gaussian. This solution comes from here. We used another way. We first copied B and V, then we calculated, we displayed the result. And this solution, in this case, we first clone B, we create extended matrix of B, then we use linear equations Gaussian algorithm. This is the second implementation. We first cloned B by extending B, then we solved the equation. This is the result. So 2, 3, minus 1, 2, 3, minus 1 is the solution. In this episode, we modified this function at this line. Then scroll down. We modified this function here. This is the same function we created in our previous episode, episode 41. We also implemented this function. This function, very similar, but a little bit different. A lot of code has been repeated. And we implemented system of linear equation using Gaussian elimination algorithm. In my next episode, we will use forwarding reference and merge these functions into a single function. And the episode after next episode, we will implement inverse matrix Gauss-Jordan algorithm. I will upload complete source code of this episode to my website. By the time you watch this episode, you can download the complete source code by clicking this link. Please subscribe to my YouTube channel. Thank you for watching.